Almost $1 billion in funding poured into the quantum computing industry last year. About half of that money went to one company, PsiQuantum. What are they building? Nothing less than a photonic quantum computer with 1 million qubits. Find out how soon this machine could change the world in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the co-founder and chief architect of PsiQuantum. I'd like to welcome Terry Rudolph to the show. Thanks for coming.
Hi, Konstantinos. Thanks for having me.
Yeah. You guys have been making a lot of buzz in the industry for a while, so I'm super excited to have you on finally. One thing just happened in the industry really recently, so I hope we could touch on it, and it might color some of where we go today. But last week in Nature, there were 3 papers published on super high fidelity qubits in silicon. So there was some, 99.87% fidelity, which is pretty close to error proof. And I know that that's sort of the approach of your company, so hopefully we can touch on a little bit of that. So while other companies have started with smaller NISQ machines, you're going for the gold here, right? You're going for the grail, 1 million qubits, boom, straight out of the gate. So do you have a rough timeline or roadmap of when that kind of horsepower is going to appear?
Yeah, so we have taken a bit of a contrary stance. I guess 5 or 6 years ago when we started the company, maybe it was possible to justify targeting NISQ machines, the noisy intermediate scale machines, which is a bit like building a calculator instead of a universal programmable computer. But we decided we really wanted to build something that could have high societal impact, and so we wanted the fully programmable machine. And that's shooting for the moon. And when you're trying to get to the moon, you have sort of 2 choices. One is you can start building things up, build a building, and then go off and invent concrete and build a skyscraper and try and get a bit closer to the moon incrementally. And our approach was very different. It was just to say, well, we've got to go off and work out how to build a rocket engine. And that's what we've been doing. Our rocket engine is basically like the quantum equivalent of a GPU would be for a classical supercomputer, sort of a GPU with some optical fibers attached to it, this kind of thing. And we, so in order to build that GPU, we, right from the start of the company, said, since we're going to need 1 million qubits, we're only going to build everything in a 300 millimeter top tier semiconductor foundry. So that this is the kind of place that builds laptops, cell phones, so that we can sort of stare down those numbers of, we've got to build 1 million qubit machine. So right now we're at the point where by the middle of this decade, we will have that core module. And then at that point, we're in a similar situation to if you were building a data center or a classical supercomputer, that you then have to assemble those modules, millions of them, to make the final machine. But so we're talking sort of middle of the decade to have that kind of core module fully manufactured in a semiconductor foundry. The other thing to say about that is, 1 million qubits sounds scary, but if you work with these top-tier foundries, they're building machines of billions of components, trillions, in fact, all of the time. So it becomes much less scary.
So you mean within 2 years, maybe, we might have 1 million qubits from your machine?
No, within a couple of years, we will have the modules, which then essentially have to be wired together, a bit like a data center or a... thing from which we can essentially scale arbitrarily far in terms of how many qubits we build.
Okay, so will these be kind of like modular approach, like University of Maryland years ago, I don't know, 7, 8 years ago, was kicking around the idea of making these little 5-qubit modules and then daisy chaining them. Are you envisioning something like that?
It's similar, because photons can be very easily daisy chained because we have this amazing technology called optical fiber, which is the way I'm speaking to you right now. And so we don't have a lot of problems of, getting the quantum states out of the atomic qubits into the photons and vice versa. So essentially, that's what we're doing. Yeah.
Okay. So like interconnect within one big machine is the idea, like interconnect on steroids in one machine.
Absolutely. It's a massive networked machine. Yeah.
And do you know roughly how many qubits would be in each of these modules that are proposed?
Yeah, I do, but I don't think I should be telling you.
Okay. Yeah, we don't try to do gotcha moments here.
We will still need a large number of those modules. It's not like, we only need a handful of those modules. We still need a large number of them. We're still building a very big machine, and I think any realistic technology has to stare down the fact that they're building something, that is going to be a large machine, consumes a lot of power and laser power and cooling power and so on.
Okay, so that gets the module, let's say by, I don't know, 2025 or something. And then how many years do you think before they're all married into this monster? And do you consider at any point maybe rolling out an interim machine that's, I don't know, 500,000 qubits or something, anything like that? Or
we certainly have engineering proof points that internally we know we need to build, systems of larger amounts of integration. Those are primarily about engineering and not the quantumness of the devices. The assembly of a final machine, well, to some extent, we start it now. It's not like we're going to have the module and then immediately go off and go, right, now we've got to pour some concrete. We're getting ready for the assembly now. But it's a long and expensive process to do it for classical supercomputers, and that's when you can go off and hire an engineering team, which have already done it. So there's always a bit more uncertainty when you're doing something which no one has ever done before. But at the same time, the components, everything we're doing is standard semiconductor components. And so other than the cooling that we have to do, we have liquid helium being pumped around this thing. I think we have a pretty fair idea of what we're facing.
Yeah, and Microsoft seems to believe in it too. That generated quite some buzz. So what kind of error correction ratios are you looking at? So the first idea of 1,000,000 qubits, it was kind of tossed around because of some pretty heavy error correction ratios, right? Like IBM was kicking, you might need 1,000 qubits to generate one logical one. Was there a number your team was shooting for or started to see evidence of maybe being the path forward?
Yeah, so we always targeted 1,000,000 qubits right from the start. That was just the number that we felt was the right ballpark to have in mind. And yeah, so IBM will say, we need about 1,000 qubits per logical qubit. And then it can be very confusing because other companies will come out, you'll hear trapped ion approaches saying, well, we only need 4 qubits for 3 logical.
To give you 3 logical, yeah, that's such a big difference.
And so the problem with this is that there's just a whole bunch of apples to oranges comparisons being done kind of along with a whole bunch of obfuscatory hype, to put it bluntly. And there's many details that kind of get swept under the rug when you just use a single number, like the error correction ratio. What we really need to know is how many gate operations can you execute with your logical qubits? So how many gates can you run? How fast are those gates? How many of those logical qubits are accessible to the user as opposed to being the kind of helper qubits that are required to run the computation? And so a sort of more meaningful way to think about the error correction ratio is to say, how many physical qubits are you going to need to be able to finish a quantum computation with a few billion operations on a few hundreds of logical qubits within a few hours? Okay, you don't want to be running for more than a few hours, a few billion operations, a few hundred logical qubits. And that's really the smallest size of quantum computation we need in order to do stuff that's genuinely useful, that we know for sure that can change the world. And it's thinking about numbers like that. That's where IBM's number of 1,000 to 1 comes from. And it's a very similar ratio in our machine. And so if you sort of put that together on the order of 1,000 logical qubits, you're basically going to need 1,000,000 physical qubits. Whereas this sort of 4 to 3 ratio, on the other hand, and stuff, this is not going to provide logical qubits that are anywhere close to being able to do a billion gate operations. And in fact, we think we need tens of billions of gate operations. So for trapped ions, it's just the true kind of usefulness ratio could be even much worse than the 1,000 to 1, because their gate operations are very slow. So they may be 100 to 1,000 times slower, just the time it takes to even do one operation on a physical qubit. And so this, so basically their equivalent of our 1 million qubit machine could be, 100 million trapped ion qubits. And this is why, of course, you don't hear them saying very much about that.
Yeah, that's a scary number. It's starting to get, considering what they have now. And when you describe it this way, it makes me think of like what Supertech's doing right now with the Supermark benchmark. This ability to run different quantum computers through actual applications to see how they perform and compare. They even consider things like reset times, how long it takes to get up and running for another shot or whatever. That is all important. So it sounds like this machine would easily achieve quantum advantage. I mean, if you just do the math, right? I mean, we'd be in a territory where we can't simulate it, but it would still be short of the 2,500 you'd need for attacking, let's say, Bitcoin, or 4,000 for the start of RSA, and then up depending on the size. So somewhere in that sweet spot. And of course, if you built a few of them and connected them, maybe overnight we do have a juggernaut, right? Like it is possible to chain these together.
Yeah, and you see that those applications that you bring out, the attacking Bitcoin, I think it's attacking the communication protocols in Bitcoin, or attacking RSA. I'm not an expert on security, but personally, I'm not keen that the first quantum computer gets used for that kind of thing, or for things that are of sort of dubious societal value, right?
Oh yeah,
I want to make sure that the things and the things that we think that a several hundred logical qubit quantum computer will be able to solve are things, fortunately, that are not like that. They're things that are important for health and climate change and material science and so on. So, fortunately, those will be the things that we use the first quantum computers on. And also, there are options for the classical security world to start using technology. In fact, they're sort of ramping up to doing that now, using technology which is immune to quantum computing attacks. So hopefully by the time quantum computers are big enough, they do have several thousands of logical qubits, so that we won't need to worry about them.
Yeah, so a lot of customers do come worried about that exact thing. Like, when these machines are a little more mature, are we immediately in danger? And I tell them the benefits will come way before. First you're gonna, optimization will be revolutionized before cryptography is attacked. Machine learning will get better, and that's the space where we can't even really predict how much of an impact it's going to have. You hear all sorts of ranging, and security uses machine learning too. So it might be better for smart networks and things like that. So how do you feel then when you see research like what's going on with Nature, and everyone's talking about the really low error rate? Do you think that a machine built on one of those technologies, do you think that might be something similar to the quest for a topological quantum computer? Do you think there are still other lower error rate ways to
those
build?
numbers look very good, but the reality is those numbers are the numbers you need to hit in order to build the million qubit machine. So if you have a gate fidelity of 99.99%, you still have a failure of one in 1,000 operations, which means you can't do 10 billion gates. You just get out noise. So we need to hit gate fidelities, and with photons we can, of 99.99%, just to be able to build that million qubit machine with several hundred logical qubits. So yeah, don't get confused here. I mean, unless they hit 99.999999999%, they're going to have to use error correction, and they're going to end up using roughly that 1,000 to 1 physical qubits per logical qubit.
Yeah, and I mean, the founders of your company, you've all published a lot of papers. It's pretty impressive, and you've been building towards this obviously for a while. Do you anticipate doing something soon just to sort of show where you are in the process, like how your qubits are faring?
Yeah, there's debate as to what extent we should or shouldn't get into that game at some level. Once you start that, it can become a big distraction.
Okay.
So we're very focused on not deviating off the critical path. If along the way, if it's a minor deviation to just build some large thing that looks impressive, we will do that. But it's not, the thing that we're building is really going off making everything that can be manufactured. It's, boring engineering if you're a physicist at some level, but hey, I can now take this thing and we're already, making thousands of wafers of components, so, hundreds of millions, much more than every physics lab of optical components has ever put together. We just got it here on a wafer. That kind of stuff is very cool if you're an engineer or a physicist who's like into having to manufacture this stuff. But it's, would be a bit more difficult to convince the editors of Nature that, hey, this is something worth making a song and dance about.
Yeah. Yeah, you have to also consider at some point IP, right? Like at some point,
we have to consider
it's not
IP,
just science anymore, right? You're not just publishing papers for paper's sake. You want to have an edge, clearly. Yeah,
it's true.
How much do you want to give away? Yeah, I can respect that. So you've hinted at this a little bit, but how would you say your approach compares to the other big two? Trapped ion, transmon. Like what kind of indicators do you have early that make you go, well, this is why it's better clearly?
Our machine, we use photons, which are, particles of light as our basic qubit. Now, the nice thing about the photons is they don't feel heat. Okay. So in principle, this is the only way we know that you can one day get to a room temperature quantum computer, because the photons don't feel heat. But something which is sort of a bit more subtle but important physics that isn't sort of a priori obvious if you're not a scientist, is that photons are the leading way to do very high speed, very clean measurements. Okay. So photons obviously move fast and move at the speed of light, but it's also that you want to be able to do a measurement on them extremely quickly. And you can do a measurement on photons much faster than any other technology. Now, the thing about measurements, and why is this important? Well, you probably know that measurements in quantum theory, they're sort of infamous for being random, and they cause this sort of fundamentally uncontrollable, what we call collapse of the wave function. They feel like a very problematic piece of quantum theory. But actually, every quantum computing approach has to use measurements because despite the fact that they're sort of random and uncontrollable, they're the only good way we have of removing entropy from the system. And entropy is noise, and the noise is the thing that's going to cause our quantum computer to start spitting out nonsense. So if you look at what, say, IBM or Google are doing, what they do is they take 4 or 5 qubits that are sort of close to each other, and they do a measurement, a 4 or 5 qubit measurement on them to remove entropy. And they repeatedly do that, and the qubits that they have are not destroyed by the measurement. So they just do, the whole computation is really just repeated measurements on these on sort of sub-ensembles of 4 or 5 qubits. But with photons, measurements are destructive. Unfortunately, you can measure them very quickly and get the answer very quickly, but the process of doing it actually destroys the photon. So that kind of architecture just doesn't work for us. Now, there's a different approach, like a different architecture that we follow, which allows us to use 2 qubit or like 2 photon destructive measurements instead of the many photon non-destructive measurements. And that allows us to, we have like a proprietary architecture basically, which allows us to use those very fast 2 qubit measurements as a way of encoding and driving a fault-tolerant quantum computation. So it's really a very different approach, just at a fundamental physical level.
And are we drifting here into the fusion-based quantum computation approach?
Yeah, so the fusion I'm talking about here is not the fusion of energy production.
Yeah,
Or,
of course. Yeah.
so
Very different headlines to be generated.
Very different headlines.
Yeah.
Do not want to be associated. So the word fusion for us has to do with a process which merges or fuses quantum states. And it's actually something which is very easy to get photons to do. So if you look, I hope you're in a room with windows, but if you look at a window and you see a partial reflection of yourself in the window, what you're seeing there are photons that have gone from you to the window, and then some of them transmit through the window and some reflect back. Mm-hmm. Okay. Now, what you can imagine is that if there's a photon on the other side of the window, so consider one that's gone from you and then reflected off the window. If there's one coming from the other side of the window that happens to be identical to the one that's reflected off, so it's got the same color and the same sort of shape and polarization and so on. That process, they sort of interfere together in the window, and that process is sort of the key part of a fusion, what we call a fusion of the two photons. And so our whole architecture is based on that kind of interference, that basically you can have we build it onto semiconductors, but it's the same thing as the window. The photons can come along and then sort of basically see a window and go off. And then much like your eye absorbs that photon and you see, whatever it is, it gets destroyed in the process of being absorbed in your eye. And in our fusion-based approach, that's what happens as well, which is why we had to design an architecture which doesn't rely on keeping all the qubits sitting there in a nice static array in some kind of cryostat, but can deal with the fact that the photons are moving very fast, they get destroyed. But the nice thing is that the gates that you do with them are as simple as building a piece of glass. It's very much simpler technology in terms of actually getting the photons to sort of interfere with each other.
Would this have any any like applications in quantum networks also?
I mean, you were sort of asking, okay, what's different about our approach? Well, I guess, one thing is that the manufacturability and stuff like this. But another is that we really get that networking for free, because optical fiber is this sort of amazing quantum memory, if you want to think of it that way, where you can put a photon in and send it for very long distances or very long times from the perspective of a photon. And so our architecture already is like essentially a networked machine. And, we can imagine extending that to bigger and bigger networks, rather than if you were building your qubits out of, ions or superconducting qubits, your best bet is probably to try and take that state and then convert it into photons and then put it into an optical fiber or something similar. Which is we call it transduction, and it's a pretty tricky technology. There are other big differences at an engineering level, because the photons don't feel heat, we can put electronics right on top of the photonic chip, which we don't have to keep the photonic chips super isolated, so we can have all of, a billion transistors sitting right next to our qubits and things like this. And there's a lot of things that we do already, which are very large scale from the perspective of quantum computing.
Because that becomes a bit of a wiring nightmare otherwise, right? Like if you can't have anything right on the qubit, it's like, I don't want to imagine a million wires, like floating into a refrigerator or something.
Yeah.
That was a really good explanation. Yeah, I appreciate that. Definitely. So it's still early and you're building this new interface. Are you already giving thoughts to the other layers of the stack for interfacing with this, like what kind of SDKs, what kind of and maybe even like a simulator from now, just so you can start to see what it might be like to address these qubits one day?
Yeah, I think there are software tools and books and things out there which can really help anyone learn quantum computing, and I would encourage people to do it. I have a book myself, Q is for Quantum. The first part of it is free. That teaches up to quantum algorithms at qisforquantum.org. And you can get, from my book or from other books, you can really get the abstract mathematical understanding of how a quantum algorithm works and where this power comes from. But what's not sort of often talked about is that when it comes to a real-world quantum computer, the compiler depends very much on the hardware. And this is true in classical computing as well. So I don't know if you remember when Apple rolled out the M1 chip, which was built on a kind of ARM architecture instead of an Intel architecture. Everyone suddenly has to go and reprogram stuff and recompile and all this kind of stuff.
Or write with an abstraction layer. Yeah. And that
Exactly.
introduces hits to performance, definitely. Yep.
Exactly. So you can go off and learn the very high level stuff from my book or some other book. But when it comes down to working out, okay, like how will I compile the problem I want to solve for a particular quantum computer, it really depends on the hardware. And because our fusion-based approach is really a different instruction set, very different to the other approaches, we can't just rely on some other quantum algorithm companies doing that. And so we have an internal team who basically work at that compiler level there, and then work with potential end users, the kind of industries, work with customers and industries that we're interested in using the quantum computer with to basically work out, look, you want to solve a problem of this size, here's the size of photonic quantum computer that you will need, here's how long it will take, and all of this stuff. So yeah, it's in some sense not possible to be just a 100% pure hardware company because no one else can actually compile for your machine. And that's why we have a bunch of people come to work with us on those kind of problems.
So do you envision then building it all the way up the stack, or at some point handing it off? Like Cold Quanta, for example, I think they got to the point where they said, okay, we can do this much, but when you want to access our machine, you're going to use Qiskit. Because like at the end, you're still going to interface with that.
No, we're going the whole way up because it just turns out that there's a lot of optimizations that you can take all the way up to the algorithmic level. Mm-hmm. And so, and to some extent, I think people live in this sort of fantasy world that they think that quantum computing will be like classical computing, where the software companies ate the hardware companies' lunch. And that's just not going to happen. When you have a scarce resource like the hardware of a quantum computer, why would I let some other software company go off and get the IP that I can get by solving these problems myself?
Okay. So how do you envision access to it then? Like right now, including one of your big investors, Microsoft, like they have their cloud environment where you can go there and access other hardware. Do you envision being available on Azure Quantum or Amazon Braket or anything like that, or just a direct to you kind of like interface?
I think until quantum computing, until we have many quantum computers and sort of an overproduction of hardware, which I think will be a long way down the track, it's not going to be something which you just dial in and get access to a quantum computer. I think that's very unlikely to be the case.
So you envision some kind of usage model for customers set like subscription or something like that, right?
I think they will need to work with us or with any hardware company really to get that compilation right, because the machines will be small, and one logical qubit extra can make a huge difference in something what you can run. This kind of stuff,
double.
So it's
double
just,
the power, yeah.
Exactly. So it's just not going to be the kind of thing where unfortunately you can hand the grad student a login key and say, "Oh, go off and solve this for a long time." There's not going to be a glut of quantum computing power.
Yeah, I'm already calling it the bottleneck. Like I do see someone's going to say, "Hey, we came up with this perfect way to do fraud detection." It's like, great, now do it real time. You can't. You can access a machine once a week for 2 seconds. Like good luck with that.
Yeah, exactly.
So we have to work out those availability issues. So it sounds like you'll be launching in a qubit range where I was going to ask you if you had any set use cases you were hoping to work on, but with the range of what you're going to launch, and it sounds like you can work on anything, really. I mean, like those numbers, you should be able to.
Well, we are definitely just, as a company policy, we're most interested in applications that we think we can tackle with a small scale quantum computer, but that have the maximum possible positive societal impact. And so when you look at that interface, you're really talking about things to do with healthcare, climate change, energy, that kind of thing. And then you can sort of broaden out from there. And so that's why, we have an applications team who work with customers on looking at different quantum algorithms, but we really target, end users who have potential applications that we think could be really important, that we can get results that really shift the needle on certain areas in which society will really benefit. And, we're less interested in the kind of security things that you talked about, or, there's plenty of other, once you've got a lot of computing power, there's plenty of other things you can do to monetize it. But, I'm a scientist, not a businessman, and I'm not personally motivated by building a large company for the sake of it.
Changing the world is a good goal, so we'll allow you to have that one. Yeah, and with that said, I really appreciate you coming on and sharing all this. I'm pretty excited to see this machine come to fruition. I've been thinking about it a lot lately, and it's fun to finally get to talk to you. I'll be sure to put info on your book and everything too in the show notes. So yeah, Terry, thank you. Really appreciate it.
Thanks, Konstantin.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. PsiQuantum is working on a photonic quantum computer that will launch with 1 million qubits right out of the gate, to be applied to quantum gate operations. Even with error correction, this could yield 1,000 logical qubits that would prove advantageous to almost any type of use case. PsiQuantum is hoping to apply the machine to some noble, impressive uses too, including climate science. The photonic approach they're taking may be very low in error when put into practice. The founders have been working on optical quantum computing basics since around 2003, and are now taking lessons learned to a new level. By focusing on a modular approach, PsiQuantum will be able to build multi-qubit modules that can be optically connected inside the box, to make a machine with a large qubit count. This may be extendable on a larger scale too. Unlike with transmon qubits, photonic qubits are already optical. It should be possible to connect them over fiber without any loss in fidelity. Imagine the possibilities of connecting a few PsiQuantum machines together one day. We're still a couple of years away from the first modules being completed, but the company's already planning on how it will make maximum use of the technology by building the full software stack right to the end user level. We've already seen a lot of performance gains from proprietary stacks in the industry, such as Qiskit Runtime from IBM, so this is not surprising as an approach. That does it for this episode. Thanks to Terry Rudolph for joining to discuss PsiQuantum, and thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on Twitter and Instagram at ConstantHacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.